Welcome to this introduction to binary isomorphous phase diagram. So part one of two-part videos. So binary means two, iso meaning same, morphous is shape or form, and phase we're talking about states of matter, solid, liquid or gases, and we're having some diagrams to show these states. So in a sort of nutshell there, binary isomorphous phase diagrams are diagrams that show the states of matter of a mixture of two substances that can take the same form at various temperatures. So they behave the same. So the substances must be what we call completely soluble with each other. So imagine two metals with the same chemical sort of properties, same sort of size atoms. They're almost interchangeable. They're not exactly the same. They have different melting points, for example, but they kind of behave like each other. So soluble. Let's have a quick look at the cooling curve for a pure substance, reminding ourselves about what that looks like. And when we cool down, we have a mixture of some water. So we have some liquid, and as liquid cools down, it reaches the melting point of the material, and all the energy exchanges go from fluid atoms or molecules combining into solid form, and we get that isotherm there. We get that constant temperature as a phase change happens. So liquid, some solid starts forming, more and more solid, all the solids formed, and it cools down. So there's a liquid, a little bit of solid, more solid being formed, even more solid being formed, all the solids formed, and it gets to cool down. And looking at that curve, we're interested in the phases which are present. So we have a liquid in this area here. We have liquid plus solid in this area over here, and of course we have solid just in that area over here. Let's have a look at insoluble substances just to see what it looks like, to get our head around this thing. So when they're insoluble, two materials, they don't like behaving like each other. They behave separately. So like water and oil, for example. If I cool down, there's a mixture of the two substances, and we can reach the freezing point, the melting point of material A at temperature A. It starts solidifying. More A starts solidifying. All the A is solidified, and then the rest of that mixture is just B. And as we reach our melting point of B, B starts solidifying, and more B solidifies until it's all completely solid, and then it can cool down further. So let's look at our cooling curve for that. The mixture of both cool down until A starts solidifying, more and more A, then all the A is in solid form, and then we can cool down further until we reach the freezing point of B, and B starts solidifying until it's completely solid and starts cooling down further. So A, more A, all A solid, B can start solidifying, more B solidifying, all the B solid, and it can cool down. So there's those two temperatures. The phases present, we have liquid A and B, so the mix of A and B. Liquid A and B together, but some solid starts forming, solid A that is, until all the A is solid. And then we have liquid B, we had the solid A beforehand, and solid B can start forming once we've reached the freezing point of B. And all the B is solid, and we get nothing but solid A and solid B. Now let's have a look at soluble substances. So two soluble substances, they can hang on with each other, they try to behave like each other. So what happens first of all? Okay, so here we are cooling down. The mix of A and B reaches the freezing point of A, but A and B hang on with each other. So B wants to hang on to A wants to hang on to B influences A, so though A wants to start solidifying, we've got to hang on for a little bit. Okay, so B says, nope, don't want to solidify just yet. They hang on to each other. And what happens? It doesn't solidify, not just yet. Okay, but eventually there is too much A there, and A says, I need to start solidifying at some point in time. So it does start solidifying, but it doesn't solidify alone. It grabs onto some B with it. So A and B start solidifying together, but not much B, because B doesn't want to solidify yet. So A with some B starts solidifying, and the process continues from there. So the solidification starts with a solid having a higher concentration of A and some little bits of B in there. So it starts solidifying. So there's a lot of A with a little bit of B in those little solid specks. So all liquid around the outside, the solid is composed of A with a little bit of B. The liquid is basically what it was to start with, but a little bit less A because more A was going to that solid form. We can cool down a bit further. We have some more specks of solid being formed, and as that's forming, more B is able to enter to it, and because I get a little bit more B in there, it starts wanting to solidify closer and closer to its melting point. So a little bit less influence of A as I start solidifying, a little bit more influence of B, so therefore it's going to start dragging that cooling curve down towards the B. So the bonds are going from fluid into solid form, so we are going to have a decrease in the rate of temperature change, but it is going to change because as we start forming A and B, okay, there's more A out of the solution, so therefore there's more B in the solution, and B wants to solidify at its melting point, so it starts dragging that solidification temperature down further and further and further. And more B starts joining the party there, and as the solids grow, you get more and more B until we get towards that B's melting point. So eventually the mixture is completely solid, but just as we start over here where B's influence said don't solidify just yet, or A's influence says, well, I'm not going to let you solidify at B's temperature because you're not purely B. So it becomes solid, 100% solid, before it reaches that isotherm for the melting point of B. And the composition is going to be the same as what we started with. So here, a certain composition of A and B, when it starts solidifying, more A than B, but more and more B joins until we have that same mix down the bottom. That was what we started with. So now we're completely solid. We don't have to be changing those from bonds back into solid bonds there anymore, so the temperature is able to cool down at a faster rate. Looking at the phases present, we have liquid. We have liquid and solid, and the solid is a mixture of A and B. And then we have that completely solid, which is allowed to cool down even further. So solid AB with a higher concentration of A when we start, and more and more B enters it until we're about the same we are exactly the same as what we started with. Mostly liquid when we start solidifying, mostly solid when we're finishing solidifying. Now let's use some different notation here. Let's use L for liquid, and rather than say a mix of A and B, let's just call it L. Now alpha, I'm going to use that to represent the solid. And the reason we use alpha, because alpha is Greek for A, and we start off with a lot more A than we do with B, so let's just call it alpha. So rather than a mix of A and solid A and B, let's just call it alpha. So liquid, liquid and solid, and solid. Higher concentration of A in the alpha, and more B starts joining it. So this is a temperature versus time phase diagram, a cooling curve for a completely soluble mixture of A and B. So let's say this cooling curve was for a mixture of 50% A with 50% B. If there is more A, then we expect the curve to look a bit more like the pure substance cooling curve for A. So if we just a little bit of B in there, okay, we're going to have that behavior like we had for the 50-50 curve, but it's going to behave a lot more like the pure substance, so closer to that A's isotherm, the melting point. We're going to drag down a little bit as we did before, and it's going to be much further away from the melting point of B because of such a high influence of A. If I add a little bit more B to the mix, I'm just going to drag that down a bit further. And if I had 100% B, no A at all, we have the cooling curve for B. If I had a little bit of A in there, okay, it's going to pull that up. If I had a little bit more A, it's going to pull it a bit further. Now we can put all this information together into what we want to be called a binary isomorphous phase diagram, but a temperature versus concentration phase diagram. So there's our 50-50. Here's our temperatures. And let's change our axis. Okay, we're interested in concentration of B. So A with a percentage of B in there. So they were the percentages that we had before, the compositions we had. The 50-50. Our two temperatures were at those points there. Okay, so they're the two important points. Let's record them. How about 90% A with a little bit of B, that curve? Okay, let's draw across, find those intersection points. So there's our 2 points we're interested in now. 25% B there. Okay, let's find those temperatures. Plot those points on our graph. Jumping all the way to our 75% B. Let's find those temperatures, plot them on the graph. We had a 90% B there. Let's find those points, plot them on the graph. Okay, so we have what's forming to be a bit of a line graph over here. Let's not forget our endpoints there. So 100% B, its melting point was obviously the melting point of B, and for A over here. And let's just draw those over there. Okay, so here is a phase diagram, a binary isomorphous phase diagram. Over the top, we have nothing but liquid. Underneath, we have nothing but solid. And in between, we have those mixtures of solid and liquid, alpha phase and liquid phase. We're going to call this line the liquidus. We're going to call this line the solidus. So anything above the liquidus is liquid, anything below the solidus is solid, anything between the two is a mixture of the two. And there we have our introduction, our first part of phase diagrams, just to hopefully get a clear understanding about what information is actually present in these diagrams.